Look up at the night sky. Those stars you see, their light has been traveling for years, decades, sometimes centuries to reach your eyes. You're not seeing the stars as they are now. You're seeing them as they were, distant echoes of light from the past. And between those stars lies mostly emptiness. Vast, cold, incomprehensible emptiness. Tonight, we're going to explore that emptiness and discover it's not empty at all. The pale blue dot. In 1990, the Voyager 1 spacecraft was about 6 billion kilometers from Earth, beyond the orbit of Neptune, preparing to leave the solar system forever. Astronomer Carl Sagan convinced NASA to turn the spacecraft's camera back toward Earth one last time, to take a photograph of home from the edge of the solar system. The image that came back showed Earth as a tiny speck, less than a single pixel wide, suspended in a beam of scattered sunlight. A pale blue dot, barely visible against the vastness of space. Sagan wrote about this image. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Every empire that ever rose and fell, every war ever fought, every discovery, every artwork, every love story, every tragedy, all of it happened on that pale blue dot, a mote of dust suspended in a sunbeam. From Voyager's distance, Earth was less than a pixel. From the nearest star, Earth would be invisible, completely lost in the glare of our sun. From across the galaxy, our entire solar system would be invisible, just another unremarkable star among hundreds of billions. This is the scale we're dealing with when we talk about space. Distances so vast that light, traveling at 299,792 kilometers per second, takes years to cross them. Sizes so large that our minds struggle to comprehend them. Numbers so big they become meaningless. The solar system seems large from our perspective. Earth orbits the sun at about 150 million kilometers, a distance called an astronomical unit. Light from the sun takes 8 minutes to reach us. Neptune, the outermost planet, orbits at about 30 astronomical units, where sunlight takes over 4 hours to arrive. But the solar system extends far beyond Neptune. Beyond the planets lies the Kuiper Belt, a region of icy bodies including Pluto. Beyond that lies the scattered disk. And beyond that, the Oort cloud, a theoretical spherical shell of icy objects surrounding the solar system, extending perhaps halfway to the nearest star. The Oort cloud marks the edge of the sun's gravitational dominance. Objects there are barely held by the sun's gravity, and it takes them millions of years to complete a single orbit. Light from the sun takes over a year to reach the outer Oort cloud. This is the boundary of our solar system, a sphere of darkness and ice extending more than a light year in all directions. And then, emptiness. 4 light years of nearly perfect vacuum to the nearest star, Proxima Centauri. 4 years at the speed of light, the fastest anything can travel. If you could somehow travel at 1% of light speed, impossibly fast by current technology, it would take 400 years to reach the nearest star. Voyager 1, the fastest spacecraft to leave Earth, traveling at about 17 kilometers per second, will take over 70,000 years to reach the distance of the nearest star. It won't actually reach Proxima Centauri. It's heading in a different direction. But in 40,000 years, it will pass within 1.6 light-years of the star Gliese 445. By then, its power supply will have long since died. It will be a silent artifact, humanity's message in a bottle, drifting forever through the void. Space is mostly empty. The distances between stars are so vast that if you scaled the sun down to the size of a grain of sand, the nearest star would be another grain of sand 4 kilometers away. And in between, nothing, just emptiness. But that emptiness is part of what makes space beautiful. The isolation, the silence, the vast gulfs between islands of matter. Each star system is essentially alone, separated from its neighbors by distances that might never be crossed. When you look up at the night sky and see the stars, you're seeing them not as they are, but as they were. The light from Alpha Centauri left that star over 4 years ago. The light from Sirius, the brightest star in our night sky, left over 8 years ago. The light from Betelgeuse, the red giant in Orion's shoulder, left over 600 years ago. It began its journey to your eyes before Columbus sailed to America. Betelgeuse might not even exist anymore. It's a massive star near the end of its life, expected to explode as a supernova sometime in the next 100,000 years. Or it might have already exploded, and the light from that explosion is still traveling toward us, carrying news of a star's death. This is one of the strange things about looking at space. You're always looking into the past. The farther away something is, the further back in time you're seeing. Telescopes aren't just seeing across space, they're seeing across time. And from our pale blue dot, from this tiny speck barely visible even from the edge of our own solar system, we look out at the universe and try to understand it. We build telescopes, launch satellites, create theories, perform calculations. We're a thin film of life on a small rock, trying to comprehend the incomprehensible vastness that surrounds us. The pale blue dot reminds us how small we are, but it also reminds us how precious this small place is. In all the vastness of space that we've observed, Earth is the only place where we know life exists. The only pale blue dot in a cosmos full of lifeless rocks and balls of gas and empty space. The planets that shouldn't exist. For most of human history, we knew of 6 planets: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. These were the wandering stars, bright points that moved against the fixed background of the constellations. Then, in 1781, William Herschel discovered Uranus, extending the known solar system. In 1846, Neptune was discovered, predicted by mathematics, before it was seen through a telescope. This was our solar system, 8 planets orbiting a single star. We assumed other stars probably had planets too, but we had no way to detect them. Planets are small and dim compared to stars. A planet orbiting another star would be lost in that star's glare, invisible to our telescopes. Then, in 1992, astronomers detected the first confirmed planets outside our solar system, not around a normal star, but around a pulsar, the collapsed core of a dead star, spinning rapidly and emitting beams of radiation. This was unexpected. Pulsars shouldn't have planets. The supernova that created the pulsar should have destroyed any planets that existed. But there they were, 3 planets orbiting the pulsar PSR B05712, worlds that somehow survived the death of their star, or formed from the debris afterward, planets that shouldn't exist, yet did. In 1995, the first planet around a sun-like star was discovered. 51. Pegasi, B, a gas giant orbiting its star in just 4 days. This was shocking. In our solar system, gas giants are far from the sun. Jupiter takes 12 years to orbit. How could a gas giant orbit so close to its star? These became known as hot Jupiters, gas giants in tight orbits, heated to thousands of degrees by their stars. They challenged our understanding of how planetary systems form. According to theory, gas giants should form far from their stars, where it's cold enough for ice to condense. How did these planets end up so close? The answer is planetary migration. Planets don't stay where they form. They interact with the disk of gas and dust around young stars, and these interactions can cause planets to spiral inward or outward. Hot Jupiters formed far from their stars and then migrated inward, settling into close orbits. This was just the beginning. As detection methods improved, thousands of exoplanets were discovered, and they were strange, far stranger than our orderly solar system suggested was normal. There are planets orbiting binary stars, 2 suns like in Star Wars, except real. Planets where it rains glass sideways in 1,000-kilometer-per-hour winds. Planets so hot that rocks evaporate on the day side and condense on the night side, creating a rain of pebbles. Planets tidally locked to their stars, with one side eternally facing the sun and the other in eternal night. There are super-Earths, rocky planets larger than Earth, but smaller than Neptune. Our solar system doesn't have any, but they seem common elsewhere. There are mini-Neptunes, small gas giants that also don't exist in our solar system. There are planets that orbit their stars in just hours. There are planets in orbit so elliptical, they experience wild temperature swings. There are planets orbiting dead stars. One of the strangest is HD 189733. B. It's a hot Jupiter about 63 light-years away, orbiting its star in just 2.2 days. The planet's atmosphere is over 1,000 degrees Celsius. Winds blow at over 8,000 kilometers per hour, 7 times the speed of sound. And it rains glass, sideways. The planet's deep blue color isn't from oceans, but from clouds of silicate particles that reflect blue light. When these particles condense, they fall as molten glass. Another strange world is 55 Cancri E, a super-Earth orbiting so close to its star that its year lasts only 18 hours. The planet is tidally locked, with one side always facing the star. That side reaches temperatures of over 2,000 degrees Celsius, hot enough to melt rock. The planet might have a lava ocean on its day side. Some scientists speculate it could be rich in carbon, possibly even containing diamond formations in its interior. Kepler 16b is a planet orbiting 2 stars, a binary system where the stars orbit each other and the planet orbits both. If you stood on this planet's surface, you'd see 2 suns in the sky, circling each other in a cosmic dance. The planet is cold and gaseous, probably not habitable, but its existence proves that circumbinary planets around binary stars, are real. Then, there are the rogue planets, worlds that don't orbit any star at all. They were either ejected from their home systems through gravitational interactions or formed independently in interstellar space. These planets drift through the darkness between stars, frozen and alone. Some might have thick atmospheres that trap enough internal heat to maintain liquid water beneath icy surfaces, creating potential habitats for life in complete darkness, lit only by starlight and the planet's own internal heat. We've found planets orbiting stars completely unlike our sun. Planets around red dwarfs, cool, dim stars that burn for trillions of years. Planets around massive blue stars that burn bright and die young. Planets around white dwarfs, the cooling remnants of dead stars. The diversity is stunning, and we've only just begun exploring. The thousands of exoplanets discovered so far are mostly large planets close to their stars. Those are easiest to detect. Small, distant planets like Earth are much harder to find. As our detection methods improve, we're finding more Earth-sized planets in habitable zones, regions around stars where liquid water could exist on a planet's surface. Some of these might be habitable. Some might have life. In the vastness of space, with hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies in the observable universe, the number of potentially habitable planets is astronomical. Even if life is incredibly rare, there should be countless worlds where it exists. But we don't know yet. We've found the planets, but we can't yet study their atmospheres in enough detail to detect biosignatures, chemical signs of life. That's the next step. New telescopes, new instruments, new techniques to analyze the light passing through distant atmospheres, searching for the chemical fingerprints of life. The planets that shouldn't exist, hot Jupiters, super-Earths, worlds around pulsars, planets orbiting binary stars, they've taught us that planetary systems are far more diverse than we imagined. Our solar system, orderly and stable with its planets in nearly circular orbits, might be unusual. The chaos might be more normal than the order. And somewhere among those thousands of discovered planets, among the millions yet to be found, there might be another pale blue dot, another world with oceans and continents and life, another place where evolution has created complexity and intelligence, another civilization looking up at their sky, wondering if they're alone. The stars that explode. Stars seem eternal. They shine steadily for human lifetimes, for recorded history, seemingly unchanging. The constellations our ancestors saw are the same we see today. But stars are not eternal. They're born, they live, and they die. And some die spectacularly. A supernova is the explosive death of a star. For a brief time, days or weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars. The explosion releases more energy in seconds than our sun will produce in its entire 10 billion year lifetime. The blast wave expands at thousands of kilometers per second, slamming into surrounding space, heating and compressing gas, triggering new star formation. There are two main types of supernovae. Type Ia occurs when a white dwarf, the dense core of a dead star, accumulates material from a companion star until it reaches a critical mass. The white dwarf can no longer support itself against gravity. It collapses, then rebounds in a catastrophic explosion that completely destroys the star. Nothing remains. The white dwarf is converted into energy and expanding debris. Type the Skudu. Supernovae occur when massive stars, at least 8 times the mass of the sun, run out of fuel. These stars spend their lives fighting gravity through nuclear fusion. They fuse hydrogen into helium, helium into carbon, carbon into heavier elements, building up layers of different elements like an onion. But fusion stops at iron. Fusing iron doesn't release energy, it consumes energy. When the core becomes iron, fusion stops. The core collapses in less than a second. The collapse is catastrophic. The core shrinks from thousands of kilometers in diameter to about 20 kilometers, the size of a city. The density becomes so extreme that protons and electrons merge into neutrons. The core becomes a neutron star, matter so dense that a teaspoon would weigh as much as a mountain on Earth. The collapse releases enormous gravitational energy. The outer layers of the star fall inward, hit the incredibly dense core, and rebound. A shock wave moves outward at a significant fraction of the speed of light. In hours, it reaches the EI star's surface. The star explodes, blasting its outer layers into space. For weeks, the supernova shines. At its peak, it's brighter than billions of normal stars. Then it fades. After months or years, only an expanding cloud of debris remains, a supernova remnant. And at the center, if the star wasn't too massive, a neutron star. If the star was massive enough, even neutron matter can't resist gravity. The core continues collapsing beyond the neutron star stage. It becomes a black hole. Supernovae are rare, 1 or 2 per century in a typical galaxy. But galaxies are numerous. Somewhere in the universe, several stars explode every second. Most are too distant to see from Earth. But occasionally, a supernova occurs in or near our galaxy, close enough to be visible. In 1054 CE, Chinese and Arab astronomers recorded a guest star in the constellation Taurus. For weeks, it was bright enough to be visible during the day. Today, we can see the remnant of that explosion, the Crab Nebula, an expanding cloud of gas still glowing from the explosion's energy. At its center is a neutron star, spinning 30 times per second, emitting beams of radiation like a cosmic lighthouse. In 1572, Tycho Brahe observed a supernova in Cassiopeia. It was brighter than Venus, visible in daylight for weeks. This observation helped overthrow the Aristotelian idea that the heavens were perfect and unchanging. The stars were not eternal. They could appear, change, and disappear. In 1604, Johannes Kepler observed another supernova. It was the last supernova visible to the naked eye in our galaxy. Over 400 years have passed since then. We're overdue for another. Modern astronomers watch for supernovae in distant galaxies. Thousands have been observed. Each provides data about stellar evolution, about nucleosynthesis, about the universe's expansion. Type Ia supernovae, because they reach a predictable peak brightness, are used as standard candles to measure cosmic distances. But here's the thing about supernova. They're essential for life. The explosion creates and disperses heavy elements. All the elements heavier than iron in the universe, including many essential for life, are created in supernovae. The gold in jewelry, the uranium in nuclear reactors, the iodine in your thyroid, all were forged in the heart of exploding stars. Our solar system formed from a cloud of gas and dust that included material from previous supernovae. The Sun is a third-generation star, made from the remnants of earlier stars. The elements in your body, except for hydrogen, were created in stars. You are made of stardust. This isn't metaphor, it's literally true. The atoms in your body were forged in stellar furnaces and scattered by stellar explosions billions of years ago. Supernovae also trigger star formation. The blast wave from an explosion compresses nearby gas clouds, causing them to collapse and form new stars. The death of one star can trigger the birth of thousands. But supernovae are also dangerous. If one occurred too close to Earth, say, within 50 light years, the radiation could damage our ozone layer, causing mass extinction. Fortunately, there are no stars within that distance that are massive enough to go supernova in the near future. Or are there? Betelgeuse, the red supergiant in Orion, is about 650 light-years away and could go supernova any time in the next 100,000 years. When it does, it will briefly become brighter than the full moon, visible even during the day. It will be spectacular and harmless, far enough away that we'll be safe, but close enough for an incredible show. The supernova that created the Crab Nebula was about 6,500 light-years away. When Chinese astronomers saw it in 1054, the star had actually exploded around 5,446 BCE. It just took over 6,500 years for the light to reach Earth. By the time humans saw the explosion, the shock wave had long since passed through interstellar space, the debris had cooled and dispersed, the neutron star had settled into its rapid spin. We were watching history, a replay of an event that happened millennia earlier. This is always true with supernovae. By the time we see them, they're already over. The explosion happened years, decades, or millennia ago. We're watching echoes, light that's been traveling through space, carrying news of stellar death. Somewhere in the galaxy, a massive star is in its final days. Maybe its core is already iron, fusion slowing, collapse imminent. Maybe it will explode tomorrow, or next week, or 1,000 years from now. When it does, the light will begin its journey toward Earth. Years or millennia from now, astronomers will detect it. A new star will appear in the sky, brightening over days, fading over months. And we'll be watching a death that occurred long before the light reached us, a star ending its life in the most violent event in the universe. The telescope that looks back in time. In December 2021, a telescope was launched into space, not just any telescope, the James Webb Space Telescope, the most powerful space telescope ever built. Its primary mirror is over 6 meters across, made of 18 hexagonal segments coated with gold. Its instruments can detect infrared light from the most distant objects in the universe. But the James Webb Space Telescope isn't just looking far away, it's looking back in time. When you look at distant objects in space, you're seeing them as they were when their light left them. The farther away something is, the longer its light has been traveling, and the further back in time you're seeing. The most distant galaxies visible to James Webb emitted their light over 13 billion years ago, when the universe was only a few 100 million years old. We're seeing these galaxies as they were in the universe's infancy, shortly after the first stars formed, when galaxies were just beginning to coalesce from primordial gas. These early galaxies don't look like modern galaxies. They're smaller, more irregular, more chaotic. They're in the process of forming, merging, growing. Star formation is intense, far more vigorous than in modern galaxies. The early universe was a more violent place, galaxies colliding and merging frequently, supermassive black holes growing rapidly, stars forming in immense bursts. James Webb can see this because it observes in infrared light. The expansion of the universe stretches light waves, shifting them toward longer wavelengths, toward the red end of the spectrum. Light that was emitted as visible light or ultraviolet billions of years ago has been stretched by cosmic expansion into infrared by the time it reaches us. James Webb's infrared vision allows it to see this ancient red-shifted light, but looking back in time with telescopes reveals something profound. The universe has a history. It hasn't always been as it is now. It was different in the past, and it's changing toward a different future. 13.8 billion years ago, the universe began. We don't know what caused it. Calling it the Big Bang is just naming our ignorance. But somehow from something, space and time and matter and energy began expanding. The universe was unimaginably hot and dense, cooling as it expanded. For about 380,000 years, the universe was opaque, too hot for atoms to form. Light couldn't travel far before being absorbed. Then the universe cooled enough for electrons and protons to combine into hydrogen atoms. Light could finally travel freely. This first light, released when the universe became transparent, is still traveling through space. Stretched by cosmic expansion, it's now microwave radiation, the cosmic microwave background, detectable by radio telescopes as a faint glow coming from all directions. After the cosmic microwave background, there was a period called the Dark Ages. No stars had formed yet. The universe was full of hydrogen gas, slowly clumping together under gravity, but not yet dense enough to ignite fusion. This lasted for tens or hundreds of millions of years. We're not sure exactly. The universe was truly dark, no light except the fading afterglow of the Big Bang. Then, gravity pulled gas clouds together until they were dense enough to ignite. The first stars formed. They were massive, much more massive than modern stars, and they burned bright and brief. They lived for only millions of years, then exploded as supernovae, creating heavier elements and scattering them into space. These first stars began reionizing the universe. Their intense ultraviolet light stripped electrons from hydrogen atoms, creating the ionized gas that fills most of the universe today. The Dark Ages ended. The universe became transparent again, but now full of starlight instead of just the fading afterglow of creation. Galaxies began forming as stars clustered together, drawn by gravity into larger structures. Small proto-galaxies merged into larger ones. Supermassive black holes. Formed at galactic centers, we still don't fully understand how. Gas flowing into these black holes released enormous energy, sometimes outshining entire galaxies. About 9 billion years ago, 4.5 billion years before Earth formed, the universe's expansion began accelerating. Something, we call it dark energy, though we don't know what it is, started pushing space apart at an accelerating rate. The expansion, which had been slowing due to gravity's attractive force, began speeding up. About 4.5 billion years ago, in one unremarkable galaxy among hundreds of billions, a cloud of gas and dust began collapsing. The sun formed at its center. Planets coalesced from the remaining disk. Earth formed, was bombarded by asteroids, cooled, developed oceans. Life began, we don't know how, and evolved over billions of years into the diversity we see today. All of this history is visible in telescopes. Look at nearby galaxies, and you're seeing them as they were millions of years ago, already mature, full of old stars, similar to modern galaxies. Look at galaxies billions of light years away, and you're seeing them younger, smaller, more chaotic. Look at the most distant galaxies James Webb can detect, and you're seeing the universe in its youth. Galaxies just forming from primordial gas. The universe is like a book, and looking into space is like reading backwards through its pages. The present is here, around us. The recent past is nearby. The distant past is far away. The very beginning is at the edge of the observable universe, barely visible even to our most powerful telescopes. But there's a horizon we can't see past. The observable universe is limited not by our telescopes, but by the speed of light and the age of the universe. Light from anything more than about 13.8 billion light years away hasn't had time to reach us yet. The universe hasn't existed long enough for that light to complete its journey. Beyond this horizon lies more universe, perhaps infinitely more, but we can't see it. We may never see it. This means there are galaxies so distant that their light will never reach us. The expansion of space is carrying them away faster than light can travel through space toward us. We are cosmically isolated from most of the universe. The galaxies we can see are our cosmic neighborhood, and that neighborhood is only a tiny fraction of what exists. James Webb is pushing our vision back to the earliest moments we can observe. But there's always further back, always earlier times, always another page in the cosmic history book, tantalizingly out of reach, telling stories we'll never read. The planet's made of diamond 50, light years from Earth. There's a star called 55 Cancri. It's similar to our Sun, though slightly cooler and older. It has at least 5 planets, detected by their gravitational effects on the star. One of these planets, 55 Cancri E, is strange even by exoplanet standards. The planet orbits so close to its star that its year lasts only 18 hours. The surface temperature reaches over 2,000 degrees Celsius, hot enough to melt rock. But that's not the strange part. The strange part is what the planet might be made of. Analysis of the star's composition suggests it has more carbon than oxygen, unusual for a sun-like star. If the planets formed from the same material, they would also be carbon-rich. On Earth, with more oxygen than carbon, carbon binds with oxygen to form carbon dioxide and other oxygen-carbon compounds. But in a carbon-rich environment, with more carbon than oxygen, excess carbon can form pure carbon structures. At the pressures and temperatures inside 55 Cancri E, carbon could form diamond. The planet might have a thick layer of diamond beneath its molten surface. Some scientists speculate that up to a third of the planet's mass could be diamond, a world with more diamond than Earth has iron. This isn't just speculation, the math works out. In high pressure, high temperature, carbon-rich environments, diamond formation is thermodynamically favored. The planet is essentially a giant diamond wrapped in a layer of molten rock, tidally locked to its star with one face eternally burning. But 55 Cancri E isn't the only diamond planet candidate. PSR J17191438 is a pulsar, a rapidly spinning neutron star, with a planet orbiting it every 2 hours. The planet was likely once a star itself, a companion to the pulsar's progenitor. When the larger star went supernova and became a pulsar, it stripped away the outer layers of the companion star, leaving only its dense crystalline core. This core is probably crystallized carbon, essentially a giant diamond the size of Jupiter, orbiting a neutron star. It's not a rocky planet or a gas giant. It's the crystallized remnant of a dead star, composed mostly of carbon and oxygen in diamond form, denser than any normal planet, a stellar corpse orbiting another stellar corpse. These diamond planets are exotic, but they teach us something about the diversity of worlds in the universe. Planets aren't just made of rock, metal, and gas. Depending on composition, temperature, and pressure, they can have exotic structures and materials we don't see in our solar system. There might be planets where it rains liquid methane, like on Saturn's moon Titan. Planets with water ice so hot it's in exotic high-pressure phases that don't exist on Earth. Supersonic ice, where oxygen atoms are locked in place, but hydrogen atoms flow through the crystal like a liquid. Planets with cores of metallic hydrogen compress so intensely that hydrogen becomes a metal. Planets with atmospheres of vaporized rock. Planets where the surface is covered in liquid tar. The universe's planetary systems are more diverse than we imagined. For every familiar type, rocky planets like Earth, gas giants like Jupiter, there are exotic variants we never predicted. Nature is more creative than our theories, and some of these exotic worlds might be common. Carbon-rich stars aren't rare. The planets around them could routinely have diamond layers or cores. Supersonic ice might be common in the interiors of Neptune-sized planets. Metallic hydrogen probably exists in the cores of all gas giants. We're just beginning to understand this diversity. Each new exoplanet discovery adds to the catalog of possibilities. Each refined measurement of a planet's mass and radius constrains what it could be made of. Each atmospheric observation reveals unexpected chemistry. But diamond planets especially capture the imagination. Imagine a world where the most precious material on Earth is the common substance beneath your feet, where mining would mean digging through diamond to reach other materials, where diamond is as mundane as rock is on Earth. Of course, no human will ever visit these planets. 55 Cancri E is 50 light-years away, a journey that would take hundreds of thousands of years at current spacecraft speeds. PSR J1529 1438 is about 4,000 light-years away, completely unreachable with any foreseeable technology. These diamond worlds will remain remote mysteries, studied from afar by telescopes, understood through calculations and models, but never directly explored. Yet knowing they exist changes our perspective. The universe is stranger than we thought, weirder, more diverse, full of worlds we never imagined, made of materials in exotic forms, with conditions alien to our experience. Diamond planets, lava worlds, ice giants, ocean planets, rogue worlds drifting between stars. The catalog of possibility is vast, and we've only begun to explore it. The sound of space-time. On September 14, 2015, two detectors in the United States, thousands of kilometers apart, detected a signal. It lasted only a fraction of a second, a brief increase in signal strength, rising to a peak, then falling away. But that brief signal confirmed something Einstein predicted a century earlier. Gravitational waves are real. Gravitational waves are ripples in space-time itself. When massive objects accelerate, especially very massive objects like black holes or neutron stars, they create waves that propagate outward at the speed of light, stretching and squeezing space as they pass. The signal detected in 2015 was created by two black holes, each about 30 times the mass of the Sun, orbiting each other at increasing speeds until they merged. This happened 1.3 billion light-years away, 1.3 billion years ago. The gravitational waves from that merger traveled through space at the speed of light for 1.3 billion years until they reached Earth on that day in 2015. The effect was incredibly small. The waves stretched and squeezed space by less than the width of a proton over a distance of several kilometers. Detecting this required some of the most sensitive instruments ever built. Laser interferometers capable of measuring changes in distance smaller than an atomic nucleus. But scientists detected it. And since then, they've detected dozens more gravitational wave events, merging black holes, merging neutron stars. Each event tells a story. The neutron star merger detected in 2017 was especially significant. For the first time, gravitational waves and electromagnetic radiation were detected from the same event. Telescopes around the world swung toward the source, catching the light from the collision. The observations confirmed that neutron star mergers create heavy elements like gold and platinum. The colliding neutron stars spray their ultra-dense matter into space, where it decays into heavy elements. But here's what's profound. Gravitational waves let us hear the universe. When converted to audio frequencies, gravitational wave signals make sounds, chirps, as the waves increase in frequency when black holes spiral together faster and faster before merging. Scientists call these sounds the chirps of merging black holes. Space isn't silent after all, it sings. Every massive object accelerating creates gravitational waves, usually far too weak to detect. But the most violent events in the universe, colliding black holes, merging neutron stars, supernovae, create waves strong enough to travel across billions of light years and still be detectable. We've opened a new window on the universe. For all of history, astronomy was based on light, electromagnetic radiation from radio waves to gamma rays. Now we can detect gravitational waves, using them to observe events that produce no light or to see through obscuring material that blocks light but not gravitational waves. Black hole mergers often produce no light. They're completely dark events, invisible to conventional telescopes. But gravitational waves pass through space unimpeded, carrying information about the collision directly to our detectors. This is just the beginning. Current detectors can see gravitational waves from the most violent events within a few billion light years. Future detectors, more sensitive and farther apart, will see events across the entire observable universe. Space-based detectors will detect waves from supermassive black hole mergers, events too low frequency for ground-based detectors. And there might be a gravitational wave background, faint waves from the Big Bang itself, created in the first fraction of a second of the universe's existence. Detecting this primordial gravitational wave background would let us see further back in time than any telescope can reach, back to moments after creation when the universe was too hot and dense for light to travel. Gravitational waves also confirm Einstein's theory of general relativity. Einstein proposed in 1915 that gravity is caused by the curvature of space-time. Massive objects bend space and time around them. Objects moving through this curved space follow paths that appear curved to distant observers. This was a radical departure from Newton's view of gravity as a force. Einstein's equations predicted gravitational waves, moving ripples in spacetime's curvature, like ripples on a pond. But Einstein himself doubted they could ever be detected. They're so weak, requiring such incredibly sensitive instruments, that detection seemed impossible. Yet we've done it. We've built instruments sensitive enough to detect changes smaller than a proton's width. We've confirmed that spacetime itself is dynamic. It can wave, vibrate, oscillate. Space isn't a static stage where events unfold. It's an active participant, bending around mass, rippling when mass accelerates. When you listen to the chirp of merging black holes, the converted audio of a gravitational wave signal, you're hearing spacetime itself vibrating. The sound isn't traveling through space. It is space, oscillating, stretching, and squeezing, carrying information about the most violent event in the universe encoded in the fabric of reality itself. The universe sings, and now, finally, we've learned to listen. The moons with hidden oceans. Europa orbits Jupiter, slightly smaller than Earth's moon, its surface covered in ice crisscrossed with brown streaks and cracks. For centuries, it was just another moon, one of 4 large satellites Galileo discovered orbiting Jupiter in 1610, proving that not everything orbited Earth. But Europa is far more than a frozen moon. Beneath its ice shell, there's an ocean. A global ocean of liquid water, possibly twice the volume of all Earth's oceans combined, kept liquid by tidal heating. Gravitational interactions with Jupiter and the other moons flexing Europa's interior, generating heat through friction. The evidence is compelling. Europa's surface is young, geologically speaking. Few impact craters, suggesting the surface is constantly being renewed. The ice shows signs of movement, cracks and ridges, indicating the shell floats on something liquid beneath. Magnetic field measurements suggest a conducting layer below the surface, consistent with salty water. Hubble space. telescope detected what appeared to be water vapor plumes erupting from Europa's surface. The ocean is probably 60 to 150 kilometers deep, beneath an ice shell perhaps 15 to 25 kilometers thick. It's in contact with a rocky seafloor. If there are hydrothermal vents on that seafloor, and there probably are, then Europa has liquid water, organic chemicals, and energy sources. Everything necessary for life as we know it. Europa isn't alone. Enceladus, a small moon of Saturn, also has a subsurface ocean. The Cassini spacecraft flew through plumes of water vapor erupting from cracks near Enceladus's south pole. Analysis showed the plumes contained water, organic molecules, and salts, material from the ocean below, sprayed into space by geysers. Enceladus's ocean is smaller than Europa's, but it's actively venting into space. Samples from the ocean are being delivered to spacecraft without even needing to drill through ice. Future missions could fly through these plumes, collecting samples, analyzing them for biosignatures. Ganymede, Jupiter's largest moon, also has a subsurface ocean. So does Callisto, another of Jupiter's large moons. Saturn's moon Titan has lakes and seas of liquid methane on its surface, and possibly a water ocean deep beneath its icy crust. Even distant Pluto might have a subsurface ocean, kept liquid by heat from radioactive decay in its core. Ocean worlds appear to be common in the outer solar system. The traditional habitable zone, the region around a star where planets can have liquid water on their surfaces, is too restrictive. Life might not need a surface ocean. A subsurface ocean, protected from radiation by kilometers of ice, kept liquid by tidal heating or radioactive decay, could be stable for billions of years. If life exists on these moons, it would have evolved in complete darkness, never seeing the sun, living in cold oceans beneath ice shells. It would probably be microbial. Simple, single-celled organisms metabolizing chemicals from hydrothermal vents. But that would still be profound. Life arising independently from Earth, proving that life isn't unique to our planet, that the universe contains other living worlds. Europa is scheduled to be explored in detail by NASA's Europa Clipper mission and ESA's JUICE mission, both launching in the 2020s. These spacecraft will study Europa's ice shell, measure the ocean's depth, search for the best places to eventually land and drill through the ice. A lander or submarine mission to Europa's ocean is still decades away. The technical challenges are immense, landing safely, drilling or melting through kilometers of ice, deploying a submarine in an alien ocean, all while operating autonomously with communication delays. But it's possible. Engineers are developing the concepts. Imagine that moment, decades from now, when a submarine deploys into Europa's dark ocean. Its lights switch on, illuminating water that has been dark for billions of years. What will it see? A barren ocean, sterile and lifeless? Or life? Strange organisms adapted to eternal darkness, clustered around hydrothermal vents, creating ecosystems independent of sunlight, proving that life can arise wherever liquid water and chemical energy exist? We don't know. That's what makes it exciting. Europa could be dead, or it could be teeming with life. Both possibilities are profound. If it's lifeless, we'll learn something about the rarity of life, about what conditions are truly necessary. If it has life, we'll learn that life is common, that wherever liquid water persists, life finds a way. The outer solar system might host more habitable environments than the inner solar system. Earth is the only place in the inner solar system with liquid water on its surface. But the outer solar system has multiple worlds with liquid water oceans, hidden beneath ice but potentially habitable. And if our solar system has multiple ocean worlds, then other solar systems probably do too. Around every star, the outer planets and their moons might harbor subsurface oceans. The galaxy could contain trillions of ocean worlds, each a potential habitat for life. Life might be common in the universe, just hidden from view. thriving in dark oceans beneath ice shells, never developing technology or civilization, but existing nonetheless. Vast subsurface biospheres that would remain undetected unless we specifically go looking for them. The universe might be full of life, and we just haven't checked the right places yet. We've been looking at planets and habitable zones, places like Earth with surface oceans. But life doesn't need sunlight if it has chemical energy. The dark is fine if you never evolved to see. The isolation beneath ice is perfect if you never needed to disperse. Europa's ocean has existed for billions of years. If life arose there, it's had as much time to evolve as life on Earth. What could billions of years of evolution produce in a dark ocean? We won't know until we look. The galaxies that collide. The Andromeda Galaxy is approaching us. Right now, at this moment, it's moving toward the Milky Way at about 110 kilometers per second. In about 4 billion years, Andromeda and the Milky Way will collide. Don't worry. Collision, in galactic terms, doesn't mean destruction. Galaxies are mostly empty space. Stars are so far apart that when galaxies merge, stars almost never actually collide with each other. They pass through the space between each other, gravitationally interacting, but not physically touching. But the collision will be spectacular. The two spiral galaxies will distort each other's shapes, pulling out long tidal streams of stars. The organized spiral arms will dissolve into chaos. Star formation will ignite as gas clouds collide and compress. The galaxies will pass through each other, separate, then fall back together, merging over hundreds of millions of years into a single elliptical galaxy. Our sun will likely survive, flung into a new orbit in the merged galaxy. Earth will probably be fine. The chances of our solar system directly encountering another star are vanishingly small. But the night sky will be transformed. Instead of a faint band of light from our own galaxy's disk, the sky will be ablaze with stars from the combined galaxies. If humans still exist 4 billion years from now, they'll witness one of the universe's great spectacles: galaxies merging. Galaxy collisions are common. They were more common in the early universe when galaxies were closer together, but they still happen regularly today. We can see galaxies in the process of merging, spirals distorted by tidal forces, bridges of stars connecting two galaxies, elliptical galaxies with shells and streams showing they absorbed smaller galaxies. The antennae galaxies are two spiral galaxies that began colliding a few 100 million years ago. Long tidal tails extend from both galaxies, filled with stars pulled out by gravitational forces. The galaxies' cores are approaching each other, and in a few 100 million years, they'll merge completely. Star formation has exploded in the collision zones, creating thousands of new star clusters. Stephan's quintet is a group of 5 galaxies, though one is actually much closer and not interacting with the others. The remaining 4 are locked in a slow dance, colliding and merging, their shapes distorted. Gas clouds colliding at hundreds of kilometers per second, creating shock waves visible in radio and infrared observations. When galaxies collide, their supermassive black holes eventually merge too. As the galaxies spiral together, their central black holes, each millions or billions of times the mass of the Sun, sink toward the center of the merged system. They orbit each other in a gradually decaying orbit, emitting gravitational waves until they finally merge in a catastrophic event that releases more energy and gravitational waves than all the stars in the universe emit in light. These supermassive black hole mergers are prime targets for future gravitational wave detectors. Space-based interferometers will detect the low-frequency waves from these events, observing supermassive black hole mergers across the universe, measuring their masses and spins, learning about how galaxies grow and evolve. Galaxy mergers are how galaxies grow. In the early universe, small proto-galaxies formed from primordial gas. These merge to form larger galaxies. Those merge to form still larger ones. The Milky Way has absorbed dozens of smaller galaxies over its history. We can see the remnants, streams of stars from destroyed dwarf galaxies satellite galaxies that are gradually being torn apart by the Milky Way's gravity. The largest galaxies in the universe are all elliptical galaxies, smooth, featureless blobs of stars with no spiral structure. These formed through multiple major mergers. Each merger disrupted spiral structure, randomizing stellar orbits. After enough mergers, the organized rotation of a spiral galaxy is replaced by the random motion of an elliptical. The Milky Way-Andromeda merger will create such a galaxy. Astronomers have even given it a name, Milkomeda. In about 6 billion years, when the merger is complete, Milkomeda will be a large elliptical galaxy, containing all the stars from both the Milky Way and Andromeda. Over 1 trillion stars slowly aging, with few young stars forming. The star-forming spiral arms will be gone, replaced by a smooth distribution of aging stars. But this is billions of years away. For now, the Milky Way and Andromeda are separate, approaching slowly, their spiral structures intact. On dark nights, far from city lights, you can see Andromeda as a faint smudge, the most distant object visible to the naked eye, 2.5 million light-years away. The light you see left Andromeda 2.5 million years ago, when early human ancestors were just beginning to use stone tools. In that light is encoded information about Andromeda's stars, its structure, its motion. Careful observation reveals that Andromeda is approaching us, that collision is inevitable. The merger that will create Milkomeda has already begun, in a sense. The galaxies are already gravitationally bound, already affecting each other's motion, already committed to their eventual union. Elsewhere in the universe, galaxies are colliding right now, spirals merging into ellipticals, dwarf galaxies being consumed by larger ones, massive ellipticals growing ever larger by cannibalizing their neighbors. The universe is dynamic, constantly changing, galaxies growing through mergers and collisions. This is normal. This is how structure forms in the universe. Gravity pulls things together. Small clumps merge into larger ones. Galaxies grow. Clusters of galaxies form. Superclusters emerge. The universe's structure is hierarchical, built from the bottom up through countless mergers over billions of years. 4 billion years is a long time, unimaginably long. The sun has another 5 billion years before it exhausts its hydrogen and begins expanding into a red giant. Earth has perhaps 1 billion years before the sun's increasing luminosity makes the oceans evaporate. By the time the Milky Way and Andromeda collide, Earth will likely already be uninhabitable, the oceans gone, the planet a scorched desert orbiting a brightening sun. But if humanity survives, if we've spread to other worlds, if we've learned to migrate as conditions change, if we've adapted to the challenges of deep time, then our distant descendants will witness the merger. They'll see the night sky transform. They'll watch Andromeda grow from a faint smudge to a brilliant splash of stars, dominating the sky, approaching, distorting, merging. They'll live through the most spectacular astronomical event imaginable, the collision and merger of galaxies, played out over millions of years in slow motion. And then, in the merged galaxy, under skies filled with stars from 2 galaxies, they'll look out at the universe and wonder what other collisions are happening in the depths of space. What other galaxies are dancing together? What other mergers are building the universe's structure, one collision at a time? The silence between stars. Space is quiet, not silent. Nothing is truly silent, but quiet in a way that's hard to comprehend. There's no air to carry sound waves. Explosions are soundless. Stars burn without crackling. Asteroids collide in perfect silence. The universe's greatest events unfold without a whisper. What we call the sounds of space, the chirps of gravitational waves, the music of planets, the song of pulsars. These aren't sounds at all. They're electromagnetic signals or gravitational waves converted to audio frequencies so human ears can perceive them. In space itself, there is no sound. This silence is profound. On Earth, we're surrounded by sound, wind, water, animals, machines. There's always something making noise. Even in the quietest places, you can hear your own heartbeat, your own breathing. True silence is nearly impossible to find on Earth. But in space, between the stars, silence is the default. If you could somehow survive in the vacuum, you would hear nothing. No matter what was happening around you, stars exploding, black holes colliding, asteroids passing nearby, you would hear only silence. The universe's great drama would unfold in perfect quiet. This silence has an upside. Space is perfectly transparent to electromagnetic radiation. Radio waves, light, X-rays, gamma rays, they all travel through the vacuum unimpeded. There's no air to scatter or absorb them. A photon emitted by a distant star will travel for billions of years through empty space, never interacting with anything, until it finally strikes a telescope mirror or enters someone's eye. This is why we can see distant galaxies, why we can detect signals from spacecraft billions of kilometers away, why telescopes can observe the entire electromagnetic spectrum. The vacuum doesn't interfere. It's the perfect medium for astronomy, completely transparent, allowing us to see across the entire observable universe. But the emptiness is also profound. Between stars, space is nearly perfect vacuum, better than any vacuum we can create in laboratories on Earth. The density is typically about 1 atom per cubic centimeter. For comparison, air at sea level contains about 1019 molecules per cubic centimeter. Space is empty in a way we can barely comprehend, and it's cold. Without an atmosphere to trap heat, objects in space cool by radiation alone. In interstellar space, far from any star, temperatures approach absolute zero, about 2.7 Kelvin, just barely above the coldest possible temperature. This is the temperature of the cosmic microwave background, the faint afterglow of the Big Bang, the baseline temperature of the universe. But space isn't completely empty. Even in the vacuum between stars, there's something. Interstellar gas, mostly hydrogen, at extremely low density. Cosmic rays, high-energy particles moving at nearly light speed. Magnetic fields, stretched and twisted by the motion of gas and the rotation of the galaxy. Dust grains, microscopic particles of carbon and silicates, formed in stellar atmospheres and supernova explosions. These dust grains, despite being microscopic and incredibly sparse, affect what we see. They absorb and scatter starlight, making distant stars appear dimmer and redder. They create dark clouds visible against the background of stars, nebulae where stars are forming, cocoons of gas and dust collapsing under gravity. The Voyager spacecraft, launched in 1977, have now left the solar system and entered interstellar space. Voyager 1 crossed the heliopause, the boundary where the sun's influence ends, in 2012. Voyager 2 followed in 2018. Both are now traveling through the interstellar medium, measuring its properties directly for the first time. What they've found is fascinating. The interstellar medium has a density about 0.1 atoms per cubic centimeter, higher than expected. It has magnetic fields and plasma waves. It's not completely uniform. There are variations, structures, boundaries. The sun is moving through a relatively warm, low-density region called the local bubble, carved out by ancient supernovae. Beyond this bubble, the interstellar medium is cooler and denser. The Voyagers are moving at about 17 kilometers per second relative to the sun. At this speed, they'll travel 1 light year in about 18,000 years. The nearest star, Proxima Centauri, is over 4 light years away. Neither Voyager is heading toward it, but if they were, they wouldn't arrive for over 70,000 years. The spacecraft will drift through interstellar space for millions or billions of years. Eventually, their trajectories will be perturbed by close encounters with stars or molecular clouds. Eventually, they might be absorbed into other stellar systems, or ejected from the galaxy entirely, or destroyed by collisions with interstellar material. But for now, they're traveling through the emptiness, silent messages from humanity, carrying golden records with images and sounds from Earth, greetings in multiple languages, music from different cultures. The records are meant for any intelligent life that might find them, but the likelihood of that is vanishingly small. Space is vast. The Voyagers are tiny. The chances of them encountering anything, let alone being found by intelligent beings, are essentially zero. They're more likely to travel for billions of years without encountering anything, until the galaxy itself changes beyond recognition. But that's okay. The golden records weren't really meant for aliens. They were meant for us, a statement about who we are, what we value, what we want to say to the universe. A message in a bottle cast into an ocean so vast that no one will ever find it, but meaningful nonetheless because of what it says about those who sent it. In the silence between stars, the Voyagers drift. In the cold and the dark and the emptiness, they carry a piece of Earth into the cosmos. They're humanity's first interstellar emissaries, traveling into a future we can barely imagine, toward destinations no one alive today will ever see. And the universe continues around them, vast and quiet and beautiful, full of wonders and mysteries, indifferent to human presence, eternal in its cycles of creation and destruction, birth and death, light and darkness. The end of everything. The universe is expanding. Every galaxy is moving away from every other galaxy, space itself stretching, carrying galaxies apart. This expansion has been ongoing since the Big Bang, 13.8 billion years ago, and it will continue forever. We know this now. For most of the 20th century, scientists debated whether the expansion would eventually stop and reverse, causing the universe to collapse in a big crunch, or whether it would expand forever. The answer came in 1998, when astronomers discovered that the expansion is accelerating. Something, dark energy, is pushing space apart at an ever-increasing rate. This means the universe will expand forever, and the expansion will accelerate. Galaxies will recede from each other faster and faster. Eventually, distant galaxies will be receding faster than light can travel through space toward us. They'll disappear from view, their light unable to reach us, redshifted into invisibility. In about 100 billion years, all galaxies outside our local group, the Milky Way, Andromeda, and a few dozen smaller galaxies gravitationally bound together, will have receded beyond the cosmic horizon. The observable universe will shrink to just our local group, merged by then into a single large galaxy. Future astronomers, trillions of years from now, will see only their own galaxy in an otherwise empty sky. They won't be able to observe the cosmic microwave background. It will have redshifted into undetectability. They'll have no evidence that the universe is expanding, no evidence of the Big Bang, no way to know that there are other galaxies beyond their cosmic horizon. If they figure out cosmology through theory, they'll have no way to confirm it through observation. The evidence will have literally disappeared, carried away by cosmic expansion. The universe will have erased its own history, but that's still in the far future. In the nearer term, the next few trillion years, the universe will change in other ways. Star formation will continue for trillions of years, but it's already declining. The universe's star formation rate peaked about 10 billion years ago and has been decreasing since. As gas is used up forming stars, and as fewer stars die and return material to space, star formation slows. Eventually, the last star will form. Stars that exist will age and die. The massive stars will explode as supernovae or collapse into black holes. Medium-sized stars like the Sun will expand into red giants, then shed their outer layers and become white dwarfs. The smallest stars, red dwarfs, will burn their hydrogen slowly for trillions of years, but they too will eventually exhaust their fuel and fade. In about 100 trillion years, the last stars will die. The universe will enter what's called the degenerate era, a time when the only remaining stellar objects are white dwarfs, neutron stars, and black holes. These objects don't shine through fusion like normal stars. They just radiate away their residual heat, slowly cooling over incomprehensible timescales. White dwarfs will cool and darken, eventually becoming black dwarfs, cold, dark spheres of degenerate matter, radiating no light. This will take trillions of years, far longer than the current age of the universe. No black dwarfs exist yet. The universe is too young. But given enough time, all white dwarfs will become black dwarfs. And given even more time, around 10 on 100 years, even black dwarfs will decay. Protons once thought to be stable might not be stable on these extreme timescales. If protons decay, then all matter eventually disintegrates into lighter particles and radiation. Black holes will be the last objects remaining. They evaporate through Hawking radiation, a quantum process that causes black holes to slowly lose mass. The rate is incredibly slow. A solar mass black hole would take about 1067 years to evaporate. Supermassive black holes, millions or billions of solar masses, would take up to 10-100 years. But eventually, even the black holes evaporate. In the end, in the unimaginably distant future, after 10-100 years or more, the universe will contain only radiation and fundamental particles, spread thinner and thinner by endless expansion. The temperature will approach absolute zero. The density will approach zero. Nothing will happen. Nothing can happen. The universe will be empty, cold, dark, and dead. This is called the heat death. Not because the universe becomes hot, but because it reaches maximum entropy. All energy is distributed evenly. No gradients exist to drive processes, no structure remains. Just uniform emptiness, expanding forever. This is the universe's far future, according to our best current understanding. Heat death. An end not through collapse, but through expansion. Not through fire, but through cold. Not through sudden catastrophe, but through slow, inevitable decay, spanning timescales that dwarf the current age of the universe by factors of billions upon billions. But here's the thing. We don't know for sure. Our understanding of physics might be incomplete. Dark energy might not be constant. It could strengthen, causing a big rip where the universe tears itself apart. Or it could weaken, allowing gravity to eventually halt expansion. Or it could change in ways we haven't predicted, leading to outcomes we haven't imagined. The universe might be cyclic, expanding and contracting repeatedly in an endless series of big bangs and big crunches. It might spawn new universes through quantum processes we don't understand. It might have properties that only become apparent on timescales far beyond what we've observed. We're extrapolating from 13.8 billion years of history into a future stretching trillions of years. That's like observing a human for 1 second and trying to predict their entire lifespan. Our predictions are educated guesses, constrained by current observations, but potentially completely wrong. But if heat death is the universe's fate, then everything is temporary. Every star, every planet, every galaxy. All structures will decay. All complexity will simplify. The universe will wind down like a clock, its energy spreading, its gradients flattening, until nothing remains but emptiness. Yet even in that far future, the laws of physics will still operate. Space will still exist. Time will still pass. The emptiness won't be nothing. It will be something, a universe in a state of maximum entropy, where nothing can happen because everything already has. And perhaps that's okay. Perhaps endings are natural. Perhaps the universe, like all things, must die. What matters is what happens between the beginning and the end, the brief flourishing of stars and galaxies and life, the moment of complexity between primordial simplicity and final entropy. We live in that moment. We exist in the brief window when the universe is interesting, when stars shine and planets orbit and life exists. We're here to witness it, to understand it, to marvel at it. The universe's ending, trillions of years away, doesn't diminish the present. It makes it more precious. We're here now, in the time when the universe is alive with light and structure and possibility. We get to see the stars, to understand their life cycles, to discover planets around them, to wonder about life elsewhere. That's enough. That's everything. The infinite horizon. We've traveled far tonight from Earth, our pale blue dot, out through the solar system with its mysterious ocean worlds, past the stars that explode and the planets that shouldn't exist, through galaxies that collide and the silence between them, out to the edge of the observable universe and forward to its far future. But there's always further, always more universe beyond what we can see, always deeper mysteries beyond what we've solved. The horizon keeps receding as we approach it. The observable universe is about 93 billion light-years in diameter, larger than 13.8 billion light-years, because space itself has been expanding while light travels. But that's just what we can observe. Beyond our cosmic horizon lies more universe, perhaps infinitely more. Is the universe infinite? We don't know. It might be finite but unbounded, like the surface of a sphere. You could travel in a straight line forever and eventually return to your starting point. It might be flat and infinite, extending forever in all directions. Or it might have stranger topologies we haven't imagined. If it's infinite, then everything that can happen happens somewhere. Every possible arrangement of atoms, every possible planet, every possible history. There would be countless copies of Earth, some identical, some slightly different, some radically different. The universe would contain infinite diversity and infinite repetition. But whether finite or infinite, the universe is larger than we can ever explore. The fastest we can travel is light speed, and that's impossible for anything with mass. Realistically, spacecraft might reach a few percent of light speed, making journeys to nearby stars possible within human lifetimes. But trips to distant galaxies, impossible. We're confined to our local region of space. We can observe distant galaxies through telescopes, but we can never visit them. They're receding from us, carried by cosmic expansion. Even if we could travel at light speed, many galaxies are already unreachable. Space is expanding faster than light can cross it. This is our cosmic isolation. We can see vast reaches of the universe, but we're confined to a tiny bubble within it. We're observers, not explorers. We can look, but not touch. The universe displays its wonders, but most will remain forever out of reach. Yet knowing this doesn't diminish the wonder. It enhances it. The universe is full of places we'll never visit, events we'll never witness directly, mysteries we'll never solve. And that's beautiful. The universe doesn't exist for us. It simply exists, vast and ancient and indifferent, full of wonders that have nothing to do with human observers. We're lucky to be here, to witness this moment in cosmic history, to exist in a universe that's comprehensible enough for us to understand, but complex enough to remain forever mysterious. We live in the time when the stars shine, when galaxies swirl, when life exists, the brief flourishing between the Big Bang and the heat death. As you drift towards sleep now, let your mind drift through space. Imagine the pale blue dot, small and fragile, carrying all human history. Imagine the sun, an ordinary star among hundreds of billions. Imagine the Milky Way, a spiral galaxy among hundreds of billions of galaxies. Imagine the observable universe, and beyond it, more universe, perhaps infinitely more, stretching forever in all directions. Imagine gravitational waves rippling through space-time, carrying news of colliding black holes. Imagine diamond planets orbiting distant stars. Imagine subsurface oceans on icy moons, possibly harboring alien life. Imagine galaxies colliding in slow motion over millions of years. Imagine the silence between stars, the cold and the emptiness, broken only by the occasional passage of ancient spacecraft carrying messages from Earth. The universe is vast. You are tiny. And yet you're made of the universe, atoms forged in stellar cores, organized by evolution into consciousness, able to contemplate the cosmos that created you. You are the universe experiencing itself, a way for the cosmos to know itself. That's profound. That's miraculous. Out of fundamental particles and forces guided by simple physical laws, the universe has created stars and planets and life and minds. From simplicity comes complexity. From chaos comes order. From lifeless matter comes living beings capable of understanding their own origins. You're part of that story. Your atoms were born in stars. Your existence is temporary but meaningful. You're here now, briefly, able to look up at the night sky and understand what you're seeing. Not gods or spirits or magic, but other worlds, other suns, other galaxies, all following the same physical laws, all part of the same universe, all connected through shared history stretching back to the Big Bang. The universe doesn't need you to exist. It existed for billions of years before you were born, and it will continue for trillions of years after you die. Your moment is brief, a flicker in cosmic time, but you're here now, and that's enough. Sleep well. The stars will still be there tomorrow, burning in the darkness, light years away, but visible to your eyes, photons that traveled across space to reach you, carrying information from distant suns. The universe will continue its slow dance, expanding, evolving, creating new structures, destroying old ones, playing out its cosmic story across timescales that dwarf human comprehension. And tomorrow, when you wake, you'll still be on the pale blue dot, still orbiting the same ordinary star, still made of stardust, still capable of looking up and wondering at the vastness that surrounds you. The universe is ancient, vast, and mysterious, and you're part of it. You belong here, beneath these stars, on this planet, in this cosmos. Rest now. The universe isn't going anywhere. The mysteries will still be there, waiting to be explored, waiting to be understood, waiting for minds like yours to look up in wonder and ask the eternal questions. What is out there? How does it work? Why does it exist? And perhaps, someday, we'll find answers. Or perhaps the questions themselves are the point, the endless human drive to understand, to explore, to push beyond the known into the unknown. The universe is calling, but for now, rest. Tomorrow, the stars will still be waiting.